A material store is to be constructed next to a 3-metre high stone wall. The roof AB and front BC are to be constructed from corrugated metal sheeting. Only 6-metre length sheets are available. Each of them is to be cut into 2 parts, such that one part is used for the roof and the other is used for the front. So that means the distance of A to B plus the distance of B to C must equal 6. Find the dimensions XY of the store that result in the maximum cross-sectional area. So we want to maximize this area here. We also want to get the maximum cross-sectional area. So we want this side of the cross-section to be X as the distance across the floor of the store. So that's this length here in this right angle triangle. This distance here is 3 minus Y, that's the length of the wall, minus the length of the front. By Pythagoras' theorem, the distance of A to B is the square root of the sum of the squares of the short sides of this right angle triangle, this here. And if we add the distance of A to B to the distance of B to C, if we add this quantity onto Y, we must get 6 meters. So this here is our constraint equation. So X and Y can't be any old values. They must satisfy this equation here. Now, what about the cross-sectional area? Well, this is in the shape of a trapezium. That is a 4-sided figure with a pair of parallel sides. The area of any trapezium is half the sum of the parallel sides. That's half times 3 plus y in this case, times the perpendicular distance between the parallel sides, which is x. So here we have a as a function of both x and y, and we want to find the values x and y that give a maximum value for the cross-sectional area. Of course, x and y are subject to the constraint involving the total length, which is 6. Now what we need to do is get a as a function of one variable only. Get a as a function of either x or y. To do that, we look at the constraint equation and solve it to make either x or y the subject of it. Now to solve this, we need to get the square root term on its own. So that's what we have here. So we subtract y from both sides, then square both sides to get rid of the square root term. If we expand out both sides and simplify, we get our equation in x and y. So this is our constraint equation. So we make either x or y the subject of this. It's easier to make y the subject, then we have no square root. So y is 27 minus x squared divided by 6. So we sub this for y into the area formula. That means we get the area in terms of x only. So this is what we get. 3 is the same as 18 over 6. We can take out 6 here to get 1/12, and simplifying we get the area as a function of x. So for different values of x, we'll get different values of a. Obviously, we're interested in the value of x that maximizes the value of a. So from previous videos, we know that the value of x that maximizes or minimizes a function is the value of x for which the derivative is 0. So we'll have a stationary point at that value of x. So we need to find a value of x that makes the derivative 0. So we need to differentiate this with respect to x, set the derivative equal to 0. The 1/12 is just a constant when we differentiate. We can leave it to one side and just differentiate what's inside the bracket. And if we solve that quadratic equation, it's an easy one to solve, we get 2 values of x. So these 2 values are the x values of stationary points for the function a. Now, since x refers to a length, that is the length of the floor of the store, this distance here, x must be positive. So even though the negative value satisfies the equation, it's not relevant here. So there's only one value that's relevant to our problem. So that's plus 3.87306. So this must be the answer. Since there's only one value, we don't have to test to see if it's a local max or a local min or a stationary point or anything like that. This must indeed be a local max. And that makes sense from the nature of the problem. There must be a combination of values x and y that maximize this area. We can confirm that this x value is indeed a local max of the function by looking at the second derivative. We know that the second derivative of a function at a local max is less than 0. So if we take the second derivative, differentiate this expression with respect to x and plug in 3.87, we do indeed get a negative value. So we found the x value of the local max of the function for the area. Now we can go and get the area. So here's the expression for the area. So we just plug in 3.87 for x and evaluate that. Actually, that's done down here. So when x is 3.87, the area is 9.6825 square meters. So this is the maximum area of the store. I forgot to get y. That's the other dimension involved. To do that, we just go back up here. There's the expression for y. So y is the height of this front wall of the store. So we plug in for x and our y value is 2 meters.